Human-machine interface, the neurophysiology of prosthetics and control. A prosthesis or artificial limb is a man-made substitute for a missing body part. Artificial limbs are widely used to assist people who have lost body parts due to birth defects, illness, accidents, or injury. No two prosthetics are the same. They need to be customized to each individual to ensure a comfortable fit. A prosthesis can be purely cosmetic, such as an artificial eye, ear, or nose, or they can be more functional, such as an artificial leg. The simplest functional prosthetics are controlled by physical cables, which mimic the action of muscles to perform movement. Our ability to move is central to everyday life. Through our understanding of neural and cortical control, prosthetics can greatly improve quality of life. The primary motor cortex is located in the frontal lobe of the brain in the area called the prefrontal gyrus. It controls motor function using neural impulses to execute movement. These impulses travel down the primary motor cortex via the cortical spinal tract and synapses on motor neurons in the ventral horn. They will continue through to the ventral roots to innervate individual muscle fibers. For example, an impulse traveling from M1 via the cortical spinal tract and exiting at C6, which relays the info to myofibrils in the bicep, resulting in contraction. Brain Control Interface, BCI, is a software communication system. It controls external devices using electrical activities generated by the brain. There are 4 components required for function of BCI prosthetics. 1. Operating control, how the system is controlled by the user. 2. Signal output, the BCI system recording brain waves and information. 3. Signal processing, the translation of information from the brain to a useful device command. 4. Device output. The device command is then administered by the BCI system. Prosthetic arms are mechanical devices created from a metal skeleton, covered in lightweight materials such as silicone or rubber. They are mainly designed to help those regain and develop their gross and fine motor skills, which are vital in our everyday lives. Myoelectric prosthetic hands operate on rechargeable batteries. They utilize the nerves and electrical impulses in your residual limb. This is used to train the prosthetic hand to contract and relax. Artificial electrodes implanted in the prosthetic socket receive electrical impulses initiated from the brain. These signals are sent to the control unit where it converts into translated commands. The electric motor in the arm will fire signals to the motor nerves, resulting in hand motion. Some electrodes can also connect to sensory nerve cells, relaying signals of touch and pressure sensors on the prosthetic hand. These sensory signals are delivered back to the control unit, travel back through the spinal cord to the brain, giving amputees a broader range of sense. This technology is based on electromyographic signals, or EMG, generated by our skeletal muscles. This is the main source for movement of the hand and feeling how much grip pressure is being applied. Over time, the brain may recognize EMG signals of the prosthetic hand as a main functional alternative to a real hand. With training, the prosthetic hand will learn to react to the signals transmitted from the surrounding muscles. Pros and cons. Human-machine interfaces, HMIs, have improved patients' quality of life in various ways. This technology has enabled amputees and brain-damaged individuals to regain control through neuroprosthesis. It has allowed people with disabilities to re-establish independence and experience an enhanced physical and mental state. Remarkably, after rehabilitation, many candidates expressed satisfaction with the range of motion and returned ability to interact with their environment. However, there are limitations associated with these assistive devices. These include a need to increase efficacy and incorporate a user-friendly control system. HMI technology has limited functions. The hardware lacks the ability to amplify, detect, and compute complex signals from the device. Naturally, these assistive devices are highly user-dependent, meaning complex neurological function is key. Therefore, the complexity of the functions and/or reception between the user and the device due to considerable impairment makes this approach difficult to execute. Future direction. Future research will aim to improve sensory sensitivity of the prosthetic limb. This will give the user the ability to distinguish an object by its shape, texture, temperature, and feel when interacting with the object. These advanced prosthetics allow amputees to experience the feeling of having a real limb that's able to feel sensation. However, they are expensive, costing up to $70,000. Researchers have found that polymer is a more affordable and cost-effective material compared to silicone. Polymers are also better suited for prosthetics due to its strength and biocompatibility. There is a lower risk of infection and serious adverse reactions when using polymer-made prosthetics. In conclusion, the future of prosthetics and human-machine interfaces is looking promising, improving quality of life for people in need.